Yes, sir.
So okay, so we had reached to particularly some conclusions. What were the conclusions? We can read up here, or that the
Mm.
conclusions were that we were observing actually the deflection in the galvanometer. Yes or no?
Yes, sir.
And that actually the deflection that we are watching here was the proof of that some current was trying to was passing through that particular loop, particular coil through which we had attached the galvanometer. True or false?
True, sir.
Yes, that is completely true. And we had also seen that if the current is passing, that ultimately that current is being developed because of the EMF. Yes or no? We had
Yeah.
reached up to that particular expression also. That there is the presence of some EMF. Only because of that, the current was passing through that particular loop or particular
Okay.
coil. Yes or no?
Yes, sir.
Okay, so that was the thing that we had seen there, and
Mm.
based over this, we had found these all these expressions. I'm not going over it in a very detail because we had already discussed it in
Yeah.
the last class. We'll just having an overview of that so that we can start up with the new class. And the Faraday, we have seen the Faraday two law, first law and the second law. Yes or no?
Yes, sir.
First law says that that means it only tells us about the presence. If a
Mm.
magnetic flux with a coil changes with time, then an EMF induces in the coil, known as induced EMF. Understood?
Yeah.
It only
Yes,
tells
sir.
us about the presence of the EMF. That
Mm.
yes, the EMF will be induced. It how much it will
Yes.
be induced, we don't know about it. Okay, that
Mm.
was not being given in that particular expression. After that, we had given it in the second expression of the Faraday, that the rate of change of magnetic flux. That means now we are quantifying it. Before that, we were just estimating it that there will be something, but what it will be actually, we don't know about.
Yeah.
Okay, but in the first expression, we had just told that if the flux will change, EMF will be induced.
Yeah.
How much it will be induced, we don't know. But
Mm.
after that, we had reached to a particular expression that EMF will be induced, and how much it will be induced, we'll get it from this particular expression. Yes or no?
Yes, sir.
So this was the complete discussion that we had discussed in the last class. Yes, you are right that we had not done the Lenz law. We had just seen the
Mm.
Faraday's second law. That and actually, remember this, that Faraday's second law tells us only about the magnitude. It tells us
Yeah.
about the magnitude of the EMF. It don't tell us that in what way that EMF will be induced. So, for suppose, let's say that this is the coil here, and there is suppose a EMF of E is being induced across it. Yes or no?
Yes. Yes, sir.
So, if the EMF or the just the very close to it, that is the potential difference that we can see that will be across it, that will be V. Yes or no?
Yeah.
Yes, Ahil, can you hear us or not?
Yes, sir. Yes, sir.
Okay, but we can't see you.
Yes, sir. Right.
So that's it, that we were here, that there is the potential difference of V applied across the uh, that particular inductor. But do you agree that if there is a potential difference of V across this, so it could be in two ways? What are those two ways? Either we can see that the potential difference is somewhat like this, or the another way that we can see that is somewhat like this. Yes or no?
Yeah. Yes, sir.
So that means two. I mean to say that which of these two terminal will be at higher potential and which of these two terminal will be at lower potential. We don't get it by the Faraday law.
Okay.
Yes or no? It only tells us about that the potential difference will be induced across it, will be established across it. But which of those two terminal will be at higher potential and which of those two terminal will be at lower potential, we are not. We don't get it by the by that particular expression only, because it tells us only about the magnitude. Understood? Is this clear to
Yes,
you?
sir. Yes, sir.
Yes, sir.
Yes or no? Any doubts in this? So you must ask it. Then we'll start with the our today's discussion.
No
No, no.
doubt, sir.
You can start. No doubt, sir.
We can start. And
Yes, sir.
you guys revised this of the last class or not, or you're just sitting it and waiting for me to discuss it here?
No, no. Did, sir.
You
Revise, sir.
did, sir. And
Yeah.
have you people completed the last class homework?
Homework?
Sir,
Yes, homework.
was there homework? Because in the portal, I didn't see homework. I only saw
Yes,
the galvanometer.
see, remember always this, that whenever the class is being taken by me, I'm not talking about the other educators, but if the class is being taken about by me, then you must will get the homework. Either it will be a single question, but you will get it. Okay.
Okay,
So
sir.
always, if you don't get it over the team, ask it from the team. They'll let you know about it.
Yes, sir.
Sure.
Okay. Because I never leave you without homework. I'll always give it to you.
Yes, sir.
Okay. Understood?
Yes,
Yes,
sir.
sir.
So that's it. And
Sir, how many classes will it take to complete this chapter?
I think tomorrow we'll be able to complete it.
Okay, sir.
Okay. Because although I can complete it today also, but by doing so, it will be just skipping some of the good questions. So I don't want to go for that. We'll do it completely if you are doing it. Okay.
Okay, sir.
So because the questions gives you the clarity about the topic. So we will discuss that also. Okay. So first of all,
Yes, sir.
what we are going to see here is that is the Lenz law. According to the Lenz law, what Lenz law says that the induced EMF from the Faraday law, what we had seen before that, what we had seen from the Faraday law, that induced EMF uh, will be
Then,
n times of d phi by dt. Yes or no? Rate of change of flux.
yes.
What is this
But
d phi by dt? That is the rate of change of flux. Yes. You were asking something?
isn't it? Yeah, isn't it minus?
Yes, that I'm coming over that particular point.
Oh,
See, right now I'm talking only about the magnitude.
mm,
So either it is plus or minus. I don't worry about that. I'll always give the answer to be in the positive form only. Understood?
okay. Yes.
If I ask you the mod of -2, what it will be equal to?
Plus or minus.
That is 2 only.
Oh, yeah. My bad.
Okay. If I had
Yeah.
placed these two long bars across anything, so whatever I place inside doesn't matter, but whatever will come outside will be positive always. This is
Okay.
the simple mathematics.
Yeah,
Understood?
yeah.
What you people are studying right now in the mathematics?
No, no, no. It's like it's long day, sir. So,
Long day?
yeah, like whole day studying. So like it's like confusing.
Confusion. Okay. So this was the magnitude of the EMF that we had discussed here. Now, from the lens law, we'll get it the way that how it is being induced. Okay, we'll get the exact expression. From the Lenz law, what it says that the induced EMF will be in such a way that it will oppose the change in the flux. What it says that induced EMF will be in such a way that it will oppose the change in flux. Understood? That means it will try to induce the EMF in such a way that the change, whatever the flux was changing across it, that should not change. And this is actually the nature's rule that nature does not want it to be get changed. Understood? And
Yes, sir.
this always happens. Whenever you will try to disturb the nature, it will always try not to get disturbed. Okay? And if we go at the extreme ends, then we have to face it. Understood? So from the
Yes, sir.
EMF, what we get, that is to be minus of n times of d phi by dt. This was the complete expression. This is the complete expression of the EMF. Okay.
Yes, sir.
But one thing I'll just tell you, and you will see me following in the above after while I'll solve the questions. I never used to consider about these minus plus signs, and you should also never ever consider about this minus plus sign. Always, first of all, see the magnitude, then decide the direction by yourself. Okay, never apply it like that. This is with the minus sign or this. in any way, in anywhere in the physics, always first of all look for the magnitude, that what will be the magnitude, then look for the direction. And I
Yeah.
always used to distribute the things in these two categories. Like while we were discussing about the magnetic field, there also we had discussed it into these two forms. First of all, one was the magnitude form, that what will be the magnitude. The second thing, just we just see it after it, that what will be the direction. Okay, this expression is only the time when something that really wants you to apply this particular thing. Okay, for example, should I give you a small question over it? Okay, let me give you a very easy one. Let's say that the flux which is a function of time, that is given to you 3t square minus 6t plus 8. Okay, and number of loops, that is, let's say I had given to you as 5. Okay, find EMF. Find the EMF. Now you should apply this. This is a very easy one. Just apply this and get the answer. This is the number of turns that I had given you as 5. Just use it and find the answer.
Or the final answer will be an equation, or
That will be okay. Let me make it more properly. Find the EMF. First of all, it will come in terms of time. Find the EMF
yeah.
at t equals to 2 seconds.
All right.
T equals to 2 seconds.
So EMF will be 30, right?
EMF will be 30. I don't know. Well, let's solve it. Yes, Region, did you got that?
Okay. Wait into it will be 40, no? No.
Let me do it. d phi by phi of t. We'll just differentiate it. If we'll just differentiate it, what will I get? I'll get as 60 minus 6.
Yeah.
Yes or no? And the differentiation
Yes,
of
sir.
8 will be
Yeah.
0.
Yes.
And what is EMF is equal to? EMF is equals to minus of n times of d phi by dt. Yes or no?
Yeah.
Yes, sir.
Minus of phi into 60 minus 6. Yes or no?
Yes.
Yeah.
It just put the value of 2 here. What will you get? 6 2s are 12. 12 minus 6 will be 6. And that will be minus of 30. Will be the answer.
Yeah.
Okay. So minus of 30 volt will be the answer here. And this will be the final thing. So actually, this question demands you to apply that particular formula. Otherwise, you'll get a very less chance to get to see these easy questions. Okay. Now what we are going to do, we are going to see that the more properly that what this actually Lenz law says. Okay, let us now you will get to understand the things more clearly. Okay, suppose that we have let me choose another pen here. Suppose that we have the loop somewhat like this, kept like this. Okay, and let me mark again the 2 points over here, that this is the A point and this is the B point. A point is towards us. Okay, so let me write it from near, and let me write denote it with some another letter. Let me this is near and this is far. Okay, understood? So this is the loop
Yes, sir.
kept somewhat in the vertical plane, somewhat like this. Okay, so F point is away from us and N point is near us. Understood?
Yes, sir.
Is this clear to you? Now tell
Yes,
me
sir.
one thing, that if I keep the bar magnet somewhat like this, if I keep the bar magnet somewhat like this, so will there be any flux link with this particular loop?
Like this, no.
There will be no magnetic field lines passing through this loop.
So there's current flowing through the loop, right? In through the circular loop,
There is a circular conducting loop that I had kept
or
like this
conducting
in
loop,
this
sir.
orientation, and
Yes.
I had taken a bar magnet, I had just placed it like over here. So will there be any
Yeah.
magnetic field line passing through inside this loop?
Yes. Yes.
Yes or no?
Yes.
Yes, it will be passing. So, but will there be any EMF induced inside it?
No.
No, the reason behind that, the flux is constant. And
Constant.
if the
Yeah.
flux is constant, so rate of change of flux is zero.
Yes.
If rate of change of flux is zero, that means EMF will be zero.
Yeah.
Or EMF will be zero, or what I can say, that the current in the loop, current in the loop, current in the loop will be equals to 0 ampere if magnet is
Awesome.
not moving. Yes or no? Or what I should say,
Yes.
magnet is stationary. That way, that means the magnet will, if it is not moving, so there will be no current inside this. But now tell me, if I take the same case again, but this time what I'm doing here is, what I'm doing here, that this was the case one that I chosen here. This was the case two that I'm choosing here. If I'm moving it like this, suppose I'm taking it in front of this. I'm taking it in front of it towards this. So now we'll do it in stepwise manner very properly. If I start moving the magnet towards the loop, what I do, that I had started moving the magnet towards the loop. Do you agree that the flux passing inside it, flux passing inside it, that means somewhat in this direction, will increase?
Yes.
Yes,
Yes
sir.
or no? That will get
Yes.
increased. If that will get increased, do you agree that the flux is changing?
Yes.
Yes.
If the flux is changing, will the EMF will be induced inside it?
Yes, sir.
Yes.
That means in this time, the current in the loop, current in the loop will not be equal to zero. Current in the loop will not be equal to zero. We are
Zero.
aware of this. But if the current inside the loop is not equal to zero, that means there is some EMF induced inside it. Yes or no? But
Yes, sir.
Yes.
there is two way that I can induce the current like somewhat in this direction or in this direction. Yes or no?
Yes.
Do you agree both of you
Yes.
with this or not?
Yes, sir.
There is two way that the current can be induced in this way or in this way.
So, but it
Okay.
should like flow to oppose, right?
Yes,
Or can it
but
flow both way?
the next question is that if the loop is somewhat like this, the north pole is like this, and the south pole is like this. Sorry, what I'm saying here. This north point is towards us, and this F point is far away from us. Okay. Now try to understand that if the current is moving like this, so if you will apply the right hand thumb rule, what will you get? If you keep the direct your thumb in the direction of the current, you will see that the inside the loop the magnetic field will be passing somewhat in this direction.
Yes.
Yes.
Yes or no? But if the
Yes.
same case I take and I apply the N this side and F this side, and I mark the loop like this with this current. So do you agree that this time the if you apply the right hand thumb rule, you have to keep this thumb in the downward direction. You will see that the magnetic field is pointing somewhat in this direction.
Yes, sir.
Yes or no? So,
Yes.
which of these two cases should we should choose to induce the current inside it? We want the that the induced EMF. We don't want it to get increased.
Yeah.
We don't want it to get increased. So, which of these two should we choose? First case or the second case?
The first case.
First one. Don't want to
The
get
first
increased,
one
right?
case. Yes, the first one in this case, because this will try to decrease the that particular induced EMF by that particular magnet. Yes or no?
Yes.
Yes, sir.
So if that particular the direction of the magnetic field will be in somewhat in this direction, that means the current that we are going to see here is will be following somewhat like this direction. Yes or no?
Yes.
Yes.
Okay, that will be following in this direction. Okay, now tell me one more thing. If the current is following in this direction, so do you guys had answered by yourself that the magnetic field due to the loop will be in this direction? Yes or no?
Yes.
Yes.
So is it not looking like that it is behaving like a magnet? right? That from which this is the North Pole and this is the South Pole. The magnetic fields are going coming out from this side and entering in this
Yes.
side. Yes or
Yes,
no?
sir.
Because
Yes.
what was happening here? The magnetic fields were going somewhat like this and trying to cover it like this. Yes or no?
Yes.
Was this happening here or not?
Yes, sir.
So that means the above loop was behaving like a magnet,
Yes.
and that was placed somewhat like this. And it should be like this only. The reason behind that, if we place the
Oppose.
North Pole here and the South Pole here, this North and this
Repel.
North are going to repel each other.
Mm.
This North
Yes, sir.
Pole and this North Pole will try to repel each other, and actually the loop also wants the same, that this particular magnet, that the bigger one that we are taking here, that this magnet should not come near me because the flux inside me is changing. And as the flux inside me is changing, I don't want it to get changed. Understood?
Yes, sir.
Yes,
Yes.
sir.
So this was the thing. This was the actually the way how we used to mark the particular loop with North Pole or the South Pole. Okay.
Mm.
Yes.
Now, actually, because what is going to happen, the person who is standing here, who will see that it will be facing like this. That is the North Pole, and this will be facing like the South Pole. Understood? But the person who is standing behind, he will see that the in front of him it is the South Pole. Okay.
Yes, sir.
So that means this particular loop was behaving like a magnet. Now let's take the same case but with a little change. Let's say that, okay, let's in this case what we are doing, this was the case second that we had taken. In this case, oh yes, what is happening? Yes. In this case, what is happening here? What is going to happen here? That we had taken the same North Pole and the South Pole here, but this time the movement of the direction that I'm choosing here is like this. Movement of the direction that I'm choosing here is this. Is this clear to you?
Yes, sir.
If this is somewhat like this, so what do you think that the magnetic field or the flux inside the loop is going to change or not? First of all, answer me.
Yeah, it will change.
It will
It will
change.
change. If it will
Yes.
change, so do you agree that there will be some EMF induced inside the loop? Yes or no?
Yes.
Yes.
There will be some EMF induced inside the loop. If the EMF is induced in the inside the loop, the current is going to pass through it. Yes or no?
Yes.
Again, we are had came across that particular one point to decide that which current to choose.
Mm.
So this time, what do you believe that first of all, tell me, as I move this North Pole or the South Pole in the backward direction, so this particular loop uh, uh, will what is happening? The flux is reducing or the increasing from the loop?
Reducing.
Reducing.
It is reducing. So what this actually will try to increase or the decrease?
Increase.
To increase. If it will try to increase, so what kind of what kind of current will flow in this particular loop?
Anti-clockwise.
That
Yeah.
will again
Uh,
see, if you are using the word anti-clockwise or clockwise, that is the reference point, that is the reference something like that. Why? The reason behind that, suppose in the previous case, if a person is standing here, if person is standing here, for this particular person, what it is, the current is in the clockwise direction or the anti-clockwise direction? Try to
Anti-clockwise.
assume it is
Anti-clockwise. Anti-clockwise.
Mhm.
anti-clockwise. The reason behind that, if you watch a clock somewhat like this, what will you find? You will find that 12 is written here, 1 is written here, 2 is written here, somewhat like this, and
Oh,
the current is moving in the somewhat opposite direction. Yes or no?
yes.
Yes.
So it will be the anti-clockwise direction. But suppose a person is standing here, what will be the case here for this particular person? He will
Clockwise.
watch 12, 1, 2,
Clockwise.
something like this. So the current is in the clockwise direction. Understood? So if you're
Yes, sir.
using the word clockwise or anti-clockwise for answering a question, you must specify the reference point also, that from which particular point you are watching that.
Mm. Okay.
Understood? Because the same
Yes,
thing
sir.
can be clockwise for one and the anti-clockwise for some another person.
Yeah.
Is this clear to both of you?
Yes, sir.
Okay,
Yes, sir.
so as we are moving it, just trying to move this magnet at the backward side, or moving away from the loop. So what is happening? The flux was reducing. And what this loop will try, it will try to increase that flux. Yes or no?
Yes, sir.
Yep.
If it will try to increase that flux, so what kind of current do you expect? Do you expect this current?
No, no.
No, the
No,
opposite.
not this current.
The opposite
Opposite.
side, sir.
What is actually happening? The opposite
It's
one.
not
Why the reason
opposing.
behind that? Because the initially the magnetic flux was going like this, and as
Yes.
it was moving, the this flux is reducing. So what it will try? It will try to
Eh,
increase this flux only.
yeah.
Yes or no? If it will
Yes.
try to increase this particular flux, so that means you are saying that the current direction should be this.
Yeah.
Yes or no? If the current
Yeah.
direction is
Yes.
this, so and the magnetic field lines are crossing like this. Yes or no?
Yes, sir.
So do you
Yes, sir.
agree that this time what is happening, that
Okay.
it is
Attraction.
behaving like a magnet placed like this, where north pole is marked here and the south pole is marked here? Yes or no?
Yes.
And actually this should be the thing, because as this magnet, this bigger magnet is trying to move away, this will try to behave like a magnet so
Attract.
that it should attract, because this north pole and this south pole are going to attract each other.
Yes, sir.
Yes or no?
Yes, sir.
Yes,
Understood,
sir.
both of you? So
Yes, sir.
ultimately, my goal is to say that we don't want this magnet to move, this bigger magnet to move. Now, I want this particular loop to behave like a magnet so that this particular magnet should not move from its place. Okay, understood?
Yes, sir.
Suppose in the case 4, what I'm taking here, that let's say what I'm doing here, that this time I'm taking this case, and let's say that this is the not this one. Okay, and let me remove this arrow also. Okay, yes, that's it. Let me place the south pole here and the north pole here, and suppose just making it like in this direction. I'm moving this particular magnet in this direction. So can you tell me that in what way this particular is this going to induce this particular loop? What will be at the left side, L side?
South
Uh,
pole.
South.
It will be south pole,
South.
because
South
we
pole.
don't want this magnet to come towards me. We want to
Yes.
stay at the same position wherever it is. So it will be south pole and it will be north pole. That means it will what kind of magnetic field will be induced? That will be somewhat in this direction,
Yes,
somewhat
sir.
Yes.
in this direction. So that means what kind of current should I apply? This one, or
Down.
should anyone else? Had I
This one,
marked it
sir.
Down. Down.
correctly?
Yes, sir.
Had I marked it correctly or not?
Yes, sir.
Yes, sir.
I'd marked it correctly. Okay, so if you'll keep the your thumb in the downward direction, you will see that the it will pass the magnetic field are passing inside the loop. Understood? This fourth case. So this will become easy for you, rather than going that long story that if we are increasing that, so we'll decrease that. So all those things. Understood?
Yes, sir.
I think we'll get disconnected for a second, and then we'll get joined back again. Yes. Once again, can you people see me?
Yes, sir.
Okay. Let me present my screen once again. Yes. So we were here. We had seen this and we had reached upon this one. Now just answer the last one and then we'll end this discussion here. We'll move on to the some another topics. Okay. Let's say that I'm placing the magnet somewhat like this. A loop is placed somewhat like this and the same thing. Okay. Uh, okay. Let me make it downward direction. Okay, so this is the case, and this time what I'm doing here is let me mark this to be again south and this to be again north, but in this time I'm moving in this direction. So if this will be induced like a magnet, so what it will be like, which pole should be at the left side?
Not.
North.
That will be in
North.
the North Pole. So we can see it very easily. That will be in the North Pole because we don't want this magnet to go far away from us. We want it to get in touch with it. Okay, stay in the position wherever it is. We don't even want it to come towards us also. We want it to stay in the position whatever you are in. Okay, so this was the case. And uh, okay, oh, this is the north and this is the south one. So this will be the thing. That means the magnetic field will be somewhat uh, going like this. Yes or no? If it is going
Yes,
like
sir.
this, so what is the direction of the current? Direction of the
Up.
current will be in the upward direction. So as this point is towards us, near us, and this is the far away from us. Okay, so this was the case that we were discussing, and we had seen this that this how used to happen. All these things. Okay. Understood?
Yes, sir.
Yes, sir.
Is this clear to you? Okay, we'll move on to the next thing. We had seen some of the formulas. Remember this? Okay, some important things. That is, first one was EMF equals to minus of n times of d phi by dt. This was the first thing. After that, we had seen that what this actually phi is. Phi is change in the flux. What this phi is actually?
Change
Phi
in
is
flux
actually
in
change in
respect
the
to time.
flux. If we are talking about some bigger difference, so what we'll write it like? We'll write it like minus of n times of phi 2 minus phi 1. Change is always final minus initial. Remember this. Okay.
Yes.
And this will be the dt time, that is change in time. Okay. Or you can write it like t2 minus t1, t2 minus t1. Okay. Or you can write it as minus of n times of change in flux divided by change in time, divided by change in time. Is this clear to you?
Yes, sir.
Okay, so these are the things that you should remember out. If you already know about E, then you can define the I also. What will be I? I equals to V by R, that is E by R. And if you divide it by E by R, that you will get minus of N times of, or you can write it in this way also, minus of 1 by R N times of d phi by dt. Okay, so these are the small things that you should, you can derive it by yourself also. Okay, is this clear to you?
Yes, sir.
And if this I, you can replace this I by dq by dt also. Yes or no?
Yes.
Minus of r times of n times of d phi by dt. If dq by dt is there, so if you cancel out this dt from both the sides, you will and integrate it, you will get this. The total charge q to be equal to minus of 1 by r times of n times of
And five.
change in flux. Yes or no?
Yes.
So these are the small things that you should you can derive it while solving the questions also, but I'm just writing it directly over here. Okay, is this clear to you?
Yes, sir.
Okay, so that's it. The next thing that we should see here is the motional EMF. That is the motional EMF. The motional EMF is one of the very important and the popular topic that you will get everywhere. Actually, what is happening in the motional EMF? Let me make a proper setup first of all. That that setup looks somewhat like this. Okay, that setup looks somewhat like open square. So can you people see the open square? Yes or no? Okay. And what is actually there? There is a rod kept somewhat like this. There is a rod kept somewhat like this. And what else is there? Let me make it with pen only. This is somewhat a rod kept it like this. And let's say what is happening that this rod, actually, let me make the rod a little more precisely. That this is the rod that we had kept here. And the next thing that I'm marking over here is that this is moving with the velocity v here. What is happening? This is moving with the velocity v here, and this is the conducting rail. It is the railing over here. This is the external rod that I had kept here. I can move it like this in the forward or in the backward direction. Okay. Right now I'm moving in the forward direction, somewhat like this, and this is the conducting rail. What is there? It's a conducting rail. If it's a conducting rail, and suppose that there is a magnetic field, what this direction shows? This direction shows the magnetic field is pointing inside.
Yes.
This direction shows that the magnetic field is pointing inside the. Oh, let me make it a little clear. This shows that the magnetic field is pointing inside it. Okay, so the magnetic field is pointing inside it, somewhat like this. Now tell me one thing, that suppose I mark some points over here. Let's say that A, B, C, and D. I'm marking the D point over here, and let us take this length to be equal to L. This length I'm taking to be L. If this length I'm taking to be L, that means actually the length of the rod is L. Okay, this small part, you can neglect this small breadth. Understood? Don't consider it as the very specific one, that what is going to happen. We are just we are just neglecting over that particular length. That is very small. Either you consider it or not consider, the length is going to be a L only. Now tell me one thing, that if this is the case over here, so is some of the flux passing through ABCD loop area or not?
Yes, sir.
The what?
Flux is passing from the ABCD loop that we are taking here. Is there any flux magnetic field passing inside it?
Yes.
The magnetic field is passing inside it. Okay, if the magnetic field is passing inside it, so do you people agree that uh, if the rod is kept straight on one of its position, so the flux will be constant? Yes or no?
Yes, sir.
Because the area is constant. What is actually how I'm
Yes.
defining this flux? This flux is being defined by B dot A.
Yep.
Yes or no?
Yes,
Have
sir.
we discussed it in the first class?
Yeah.
This
Yes.
flux is being defined by B dot A. So if this is defined by B dot A, so actually, while if the rod moves, this A is going to change.
Yes.
Yes or no? Because if this
Yes.
rod moves, so what is going to happen? The area of this loop ABCD is going to change.
Yes.
But at the time when the rod is not moving, so is there any EMF will be induced in it or not?
No. No.
No, there will be no EMF induced in it. You are correct, absolutely correct, because the flux is not changing there. But as the as this rod starts moving ahead with the velocity v, so do you agree that there will be change in the flux because the area is changing?
Yes.
Yes, sir.
If the
Yes.
area is changing, so do you agree the flux is changing, and because of the change of the flux, the EMF will be induced?
Yes, sir.
Yes or no?
Yes.
The EMF will be induced.
Yes.
Yes, you are
Induced.
right. So if the EMF is induced here, so we can find out that particular EMF. We'll try to find out that particular EMF. So how we can do so? Actually, what is happening? This area is not fixed. This is the variable area. As the way it is moving with time, this area is going to change. Yes or no?
Yes, sir.
Yes, sir.
Okay, and how you can define this area? You can define this area to be length into breadth always. One will be the length, another will be the breadth.
Yeah.
And if I write more properly, one of the length will be V into T, and another length will be L. Speed into time, that will become the distance.
Yes.
Yes or no?
Yes, sir.
So will that area will become like this, V into T divided by into L. This is one of the length, one side of the this particular rectangle. This is the another side of this rectangle. Yes or no?
Yes, sir.
So the final flux that we are going to write here is that will be B into V into T. Actually, let me write L first, then T. Okay, so is this going to be the variable flux through this loop? Yes or no?
Yes, sir.
Can you see
Yes, sir.
that this flux is depending over the time? That
Yeah.
means the flux will change with time. So EMF will be induced. I'm talking only about the magnitude only. Okay, I'm talking
Yes,
only
sir.
about the magnitude. EMF will be uh, n times of d phi by dt. Yes or no? And this
Yes,
n
sir.
is nothing but one because there is one loop we are considering over here. Yes or no?
Yes, sir.
One turn is there, so we are considering n to be one. So we'll get the EMF to be equal to d phi by dt. Is this okay?
Yes, sir.
And
Yes, sir.
if I differentiate the above expression BVL into into time, so what will I get? I'll get BVL into dt by dt. Will that be equal to 1? Because BVL is a constant quantity.
Yeah.
Yes.
So what it will become? EMF will be become equal to BVL.
VVL.
BVL.
Okay. But I'm still not satisfied with this EMF. I'm still not satisfied with this EMF. The reason behind that is that uh, uh, now I know that there will be some potential difference across this AD rod that talking about. I'm talking about this AD rod only, and I know that there will be some EMF will be induced across it. That one of the point A or D will be at higher potential, and the another will be at the lower potential. Yes or no?
Yes, sir.
But I'm still unable to find that out that what it actually is, which of them is at the higher potential and which of it is at the lower potential. Yes or no?
Yes, sir.
So how should we get it? How should we uh, get that this particular thing is there? So now see, now try to understand we how we are going to decide it that which of the particular thing is at higher potential, which of the is at the lower potential. See, people used to use it like that using the some right hand type rules, but I'm not going to use it over here. I'm going to tell you the basic thing that is happening here at the molecular level. Based over that, we'll decide that which of the terminal will be at higher and which of the terminal will be at lower. Okay. Acha, tell me one thing. While this rod is moving, do you agree that this rod consists of positive and the negative charges that are being clubbed together? Because this is uncharged. That means the number of positive charges will be equal to the number of negative charges. Yes or no?
Yes, sir.
If these charges are there, so as this rod is moving with a velocity v in this direction, so do you people agree with me that these positive and negative ions are also moving in this in the same direction as of the v?
Yes, sir.
Yes or no? Yes, region.
Yeah.
Okay, so these positive negative charges are also moving in the same direction. And what happens if a charge moves in a magnetic field? Is there any expression of the force?
Sir, force will be
Q
Negative.
into
QVV. V into B.
V cross B?
Yes.
Was
Yeah.
this the expression of the force or not? Yes, Region Ahil,
Yes,
both
sir.
of you.
Yes, sir.
Yes, okay. If it is there, we'll apply it and we'll get the direction. How? Let's see. First of all, tell me that is the direction of the magnetic field in the downward inside the plane
Yeah.
Yes.
and V is in this direction.
Yes.
if you see V cross B, do you think that the force over these positive charges will be in this direction?
Downward.
And
Yes, sir.
force over this negative charge will be just opposite of that.
Yes.
So do you agree that all the positive ion will get accumulated at this particular side and all the negative ion will get accumulated over this side?
Yeah.
That
Yes, sir.
means what I can say here, had I got the result that this rod that I was talking about will behave like a potential
Okay.
difference of EMF
Mm.
E looking like this.
Yes, sir.
Yes
One
or
doubt,
no?
sir.
Yeah. Yeah.
Yes.
Sir, negative charge is also moving in the same direction, right? So how is it? How is the force upward?
Negative charges are also moving in the same direction. Okay. So this is the negative charge. This is moving in this direction V, and this is the magnetic field B pointing inside. Yes or no?
Yes. Yes,
Don't you
sir.
think that while writing the force, you will, this time you will not take Q, you will take minus of Q. So V cross
Oh,
B is
yes.
going to point in the same direction, but
Yes,
as we had
yes.
placed the minus sign in front of it, the force will get inverted.
Yes, sir.
So ultimately, what is going to happen? The force over the negative charge will be in the opposite direction. V cross B will be same both for both the things, positive as well as for negative. But in one of the case, you will take outside the V cross B as plus Q, but for the second case, you will take it as a minus Q. So the force will be opposite, will become
Yes,
opposite
sir.
of V cross B. Or
Yes, sir.
if you go into much more complex, just put this minus sign inside, what you will get? Q into B cross V.
Yes, sir.
Now, if you do the V cross V, you will get the opposite. Although no, it's not required here. So ultimately, did you understood that why it is negative in the opposite direction?
Yes, sir.
Yes. So the plus charge will accumulate here, and the negative charge will accumulate here. So EMF will be induced somewhat like this. Yes or no?
Yes, sir.
Yes. So we had got this result, but still, I'm not satisfied because I'm able to get the EMF. Uh, uh, but there is an issue. The issue is that I have to do this calculation separately using these rods and using this expression of force equals to Q into V cross B. That means I have to work at the two places. One will be of finding the magnitude. After that, I'll play this all the story of plus sign and minus sign moving in the same direction. Yes or no? That means we are just separating it into two things and then we are trying to solve it. So what I want is that we should do something like so that I should get the EMF directly from this particular expression or by doing it the once. Understood what I mean to say here?
Yes, sir.
I mean to say here that what should be the value how should I choose it? So let's see that how we can choose it over here. Actually, tell me one thing that if we do V cross B, if we do V cross B, uh, what will I get? If we
V
do
cross
V
B over
cross
here.
B, yes,
Force. So it'll be downward, right?
it will be in the downward direction. And if it will be in the downward direction, so uh, uh, okay, I think we'll back to this, but not the right time to get back to over this. We'll be back to over this problem and we'll try to solve it in the one expression only. Okay, but for the right now,
Okay.
let's leave it over here only that we had found out the magnitude and we are getting the direction by doing a some separate calculation. Okay,
Yes, sir.
but ultimately our goal is to get the EMF from the one expression only with the direction.
Okay, sir.
Understood?
Yes.
So we'll
Yes.
get back over this, but for the time being, let's leave it the discussion over here only because the required one we had already completed. Okay.
Yes, sir.
So let it be like this. And because I want to just give you a clarity about something else, after that we'll be moving over that so that you will be able to understand it with a little much more clarity. Now see, we have seen this that now we had reached to something that if a rod is moving somewhat like this in the magnetic field, so what we had got that if a rod is conducting rod is moving in a magnetic field, there will be EMF induced inside it. Yes or no?
Yes, sir.
Yes, sir.
Understood. And actually, the true thing that I want to say here is that suppose if there is a magnetic field somewhat kept like this, there is a magnetic field somewhat kept like this, and I'm keeping the rod, I'm taking the rod that is placed somewhat like this, okay, whose length is L, whose length is uh, whose length is L, and suppose this magnetic field was B here, and this length is moving with a velocity V. This rod is moving with a
So,
velocity V. So, will the EMF induced in this case also?
no, no, sir.
EMF will be induced. EMF will be still induced in it. But in this case, there will be no current inside this in this particular rod. The reason behind that, it is not a closed loop. Understood?
Yes.
The EMF will be still
Okay.
here.
Oh,
Understood?
yeah.
So EMF will
Mm.
be still here, but the current will
But no
not
current.
flow. Yes.
Okay.
So it will behave like now. Can you tell me that how can I replace this particular rod with exact sign of battery sign inside? I mean to say that exact this notation. That how can I do so?
Sir,
Where the
sir, I
positive
didn't
charge
get
will
it.
accumulate
Oh,
Up,
oh, so the positive charge will accumulate.
up.
Oh,
upward
yeah.
or downward? Upward. So
Yes.
it will be replaced somewhat like this.
But
Yes.
sir,
Understood? So
the positive charge, right? It depends on the person, like where is it placing, no? So is it always gonna be like
no, 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 no. It's not a reference dependent. Like if you are solving or I am solving or whoever it is solving, it will always,
mm,
for to find the force, it will always do the V cross B. So if
okay,
you'll do the V cross B, just do the V cross B. Just keep your fingers in the direction of V and turn it, curl it towards B. You will get the direction to be in the upward direction. Just keep your hand somewhat like this, towards V, and curl it inside because the magnetic field is pointing inside. So you will get the
yes,
direction to be in the upward direction.
okay,
Okay, so the EMF will be still there, but there will be no current flow in this.
yeah,
Understood? So this
yeah.
will be
Yes, sir.
the case here actually. And let's take the another case. If a rod is rotating with angular speed omega, what is happening here? This time I had taken one some different kind of a thing, that there is this x, suppose, and let me make somewhat ring-like structure that is like this. And what else is here? Let me make it a little more clearly. Mm, I'm just doing it with a dashed line. Okay, I'm just drawing it with the dashed line. Okay, so we are this there is something, let's say there is a length L rod that we had taken here. Okay, it is moving in this vertical plane omega. Uh, uh, will there be any EMF?
Sir, the dotted lines, what were the dotted lines again?
It is just a trajectory of this
Okay.
rod. Actually, it is
Yes.
rotating. That's why I had drawn it that it is rotating somewhat like this. So, will there be any
Sir, what about
EMF?
the so the rod has current flowing inside it, or
Yes, actually, let's say I had not given you the magnetic field now. So, how can you say
yeah,
about the
yes,
flux
sir.
lines? So,
That's why I
actually,
was
let's say the magnetic fields are somewhat in this direction. Actually, what is going to happen if I take the bead in the upward direction? Only the direction of the EMF induced will be changed. Magnitude is not going to change. Okay, if you
Yes.
are just inducing the battery like this, instead of this, you will apply it like this. If I change the magnetic field, one of the thing is going to, only the direction is going to reverse. Understood?
Yes, sir.
So that's why not need to worry about the direction of B. That actually doesn't matters a lot till the time we are not concerned about it. Okay, so this is going to happen. See, I'll give you a simple explanation that how to decide whether the EMF will be induced or not. Uh, Consider these magnetic field lines are like noodles. It are like noodles that are going just from the top to the bottom. They are the long ropes. And if anyhow any conducting rod cuts them, any conducting rods you find it to be cutting them, then the EMF will be induced. Understood? You just see it like this only. Never go into that story of that the area and the flux and all those things will change. Just decide it that whether is it cutting that particular threads or whatever you say. If it is cutting that, then the EMF will be induced. Okay.
Yes, sir.
So
So EMF
now
will be
first of all
induced.
decide EMF will be induced. Yes, exactly.
Yes.
So if the EMF will be induced, so yes, the again question is same that what will be the E here? First of all, the magnitude and then the direction. I can give you the direct expression of that particular thing, that how to find the direction. But I don't want you to go for the things that you should remember. If I'll give you the formula, na, you will apply it directly and find out the direction. But I don't want you
Yes,
to
sir.
do so. Solve it so that you should never get confused in the exam. If you even forgot the about the direction, you should do it like this only with the same some already learned formulas. Okay. Now, if we want to find out the EMF, how will we do so?
Sir, so over here,
Do you agree
Continue
that
bit.
here every point is not rotating with the velocity v? Every point over this rod is moving with some different velocity, but the angular velocity is same. Do
yes,
you agree that the linear
Yes, sir.
yes, sir.
velocity is not same? This point marked over here will be moving a little slower as compared to this point marked over at the extreme ends,
Yes, sir.
Yeah.
because both the points are covering the distance of 2 pi r only in the same time. Sorry, both that this point that this small one. Let's say that I'm marking this small point. This will cover a small distance in the same time, and this will cover a large distance in the same time. So
Yes,
the outside point is moving with a larger velocity, and the inside larger actually I should say speed, and the inside point is moving with a lower speed. Yes or no?
yes, sir.
Yes, sir.
So you can't take it to be VBL, because in the previous case, all the particles were moving with the same velocity V, all the particles
Yes,
over
sir.
the length L. This time it is different. So do you agree that I need to integrate the things over here?
Yes, yes,
Okay. So suppose at a distance X, at a distance X, I'm taking a small element dx. Okay.
okay.
Now tell me one thing, that if I take this small length dx, okay, so what my EMF should be equal to? What my EMF should be equal to? EMF should be equal to VBL. Yes or no?
Yes, B is constant and
Yes, B is
so
constant. And instead
yes,
of L, should I take X?
Yeah.
yes,
Because we are taking this variable length X. And what should I write for V? Okay.
V.
Wait,
Sir,
wait.
X
Uh,
is
Yes,
yeah,
exactly. X should not be taken. Dx should be taken here, because this is
yeah,
the small length that we are taking.
yes, sir.
Okay. This is the small length that we are taking over here. Understood, Rajan?
Yes.
Because this is small length that we are taking. Previously, it was the complete length L. This time we are taking this small length dx.
Yes.
Yes.
Okay. And now tell me what will be the V here? V of X actually. What will be the velocity here?
So it will be B into dx.
Velocity, do you know that formula, that velocity equals to r omega for a circular motion? If a particle at a distance r is moving with an angular velocity of omega, it will have a velocity v equals to r omega.
Okay, sir. Yes.
Yes or no?
Yes, sir. I think we've
This
learned
is
that
the
before.
yes, that was something that you must have learned in the
11th.
circular motion. Okay, in the 11th
Yes.
class. Yes. So Vx will be actually x into omega. That this is the central distance x and the omega here. Yes or no?
Yes, sir.
Yes, sir.
Okay. And that will be the thing. That's it. After that, just place it over here and you will get the relation b. And instead of, first of all, I'm writing this x omega here and then dx here. Yes or no?
Yes,
Yeah.
sir.
Is now I'm in the correct position to integrate it because omega is constant, b is
Yes.
constant, only x is the variable.
Yes.
So actually, this is the small de, and this is the small de. And if I integrate it at both the sides, what will I get? From 0 to what should be the limit?
0 to
X.
total.
0 to, from which we have to vary the x whenever we are putting the limits now. Always keep in mind that we are varying the x from which point? From the center point to this extreme point.
So total length.
Yes, sorry. This will be the L here, and what will be this dE from 0 to E. Okay,
Yes.
so in the LHS side, you will get E, and B omega will be here, and X dx will be here from 0 to L. Okay, yes, Rian, tell me
Yes.
that what is the integration of X dx?
X square by 2.
Yes, X square by 2. So that will be B into omega into X square by 2. And if I place the limit from 0 to L, that will be EMF E. And the next thing that we should write here is that EMF E equals to B omega L square by 2. Yes or no?
Yes, sir. Yes, sir.
And can you see an amazing thing here that previously it was uh, okay, let me convert it into the form of velocity. Then you may be able to. What is happening here? Suppose what is the velocity of this extreme end particle? Is it omega into L?
Yes, sir. So it'll be maximum.
Yes, it will be
Uh-huh.
maximum. It will be omega into L. So let us represent this to be with V. So what will I get if I represent it with V? So EMF will be B and omega into L. I'm separating it over here and L divided by 2. Yes or no?
Yes, sir.
Yes,
So
sir.
it will be, is it looking like VBL by 2?
Yes.
Yes, sir.
So is it the half of the previous case?
Yeah.
Yes, sir.
Yes, it is actually the half of the previous case. Why so? Because there are the sum of the particle which are moving with a very high velocity, and there are the sum of the particle that are moving with a very low velocity. So ultimately, their summation had become the half of that.
Yes, sir.
Understood? So this is the case here. Now tell me one more thing that how how this EMF is going to be. What will be the direction of the rod? That how should I replace it with the equivalent battery?
Sir,
That is good.
Who positive charges will accumulate towards the center or away from the center?
it will velocity. So velocity is towards
Velocity
it's
is away from us.
away from
Away
us.
Velocity
from.
is
Okay,
away from us.
so
It is the circular thing, so going like this, and
yeah,
velocity is away from
so
us
it'll positive charges will be towards the center.
towards the center. How we'll get? We'll get it as V
V
cross
cross
B,
B.
V cross B, and we'll get the positive charges to be get accumulated at this side, and the negative charges will get accumulated at this side. Understood?
Yes, sir. Yes, sir.
Is this clear to both of you?
Yes, sir.
Yes, sir.
Okay. If I oppose the B, then
Oppose different direction, right? So it'll be positive charges
only
towards the end.
towards the end, it will be separated like this. Because now in this case, if you do the V cross B, you have to do V cross B like this. V will be in the inside direction and B will be pointing upwards. Understood?
Yes, sir.
So that will be the case. Ultimately, this is not our concern right now. That is the easy one, very. Okay. Now suppose the third case that I'm taking here is rotating disk. What I'm taking here, that we are considering about the rotating disk. So if I'm considering the rotating disk, then what is going to happen? Try to guess, try to estimate the thing that what should I do here?
It's rotating about its plane, right?
Yes, exactly. It is rotating like this. I think you can understand easily. It is rotating like this.
Yes.
And let's say that I'm placing the magnetic field to be in this direction. What should be the EMF here in this case? Suppose I had given the length to be the same as the previous one. Previous one I had taken the L, that's why I'm taking the L to be here also.
So it will be the same, right?
It will be
The same.
No.
same. Yes, Region, what do you expect? To be same or so
That's
different?
Oh,
Hmm?
so the disk is like full. Like, is it like
It is the solid disk.
solid disk? Okay.
Yes, it is the solid disk over here. So what is going to happen?
So in the previous case, it was just the loop,
That's
right?
the single rod that was of the same length L, and it was rotating like that.
Okay. So
But in this case, it is like this.
So the velocity will be like same over the
Yeah, yes. Actually, it is
this one.
still moving with the same angular velocity omega. Okay, I had taken all the things to be of the same as the previous one, but this time the only thing that I had changed, I had taken the disk over here. So what is going to happen? I'm just concerned about that.
sir, will there be any current that's produced or no?
Uh, that I mean to ask you that if there, first of all, answer me that whether the EMF will be induced or not. Then we'll decide
EMF
that
will be
whether the
induced.
current will be
Yeah,
EMF
it will
will
be
be
EMF
induced.
will
induced.
be.
Okay. And
Yes.
what will be the magnitude of that EMF?
Magnitude will be uh BVL by 2, right?
BVL by 2. Rather than using that particular expression BVL by 2, we should use B R square by 2, whatever it was, B omega L square by 2.
V omega L square root. Okay.
Okay, because V actually, so if you are using it VBL by 2, so you should know about that, that V velocity is of the extreme point.
Yes, sir.
Okay. So what should be the EMF in this case in this disk?
Uh, B omega square L by 2, right?
You are saying the answer to be the same one as the above. Yes, Rijan, what
Yes.
do you expect
Uh, yeah.
to be
So will the
same?
disk it will be same?
It will be
So
same
like
as the above. One of the person had already said that it is same, so it is same. No.
no, I don't know. Like the point over near the rod is this, right? So the disk
Yes.
at the edge will like move faster than the no at the closer
Yes,
one.
exactly.
So
That is going to happen.
then it will be same then.
But how? Okay, let explain it to me, any one of you, that how we are getting it to be same,
Will
or
it
why
Like
will
you are saying
area?
it to be same. Hmm.
so we'll take the point over there, same as the before, like as dx and like
Okay, you are saying to do the calculation, so I'm taking the, but how you are going to do that? Yes, I'll first of
So
all, you are
will it
explaining
be
something.
like the integration of that like one length is moving?
One
Will that
length,
come into picture? Because it's like whole. It's like the area that's playing a role here, right? Like
actually, this will be again same VBL by 2, or whatever you say, omega B L square by, yes, omega B L square by 2. The reason behind that is
omega
not
square
omega
BL,
square,
right?
it is, uh,
Oh, okay.
I'd written it
L
correctly.
square. Yes.
Okay. I just replace some of the terms, rearrange some of the terms actually. What it was, B omega L square by 2. Okay, now it's fine. So actually, it will be same. The reason behind that is what is happening here. If this is the circular disk, I'm looking from the top view. it will be the collection of lot of the rods like this.
Yes.
It will be the collection of the lot of rods like this, and each rod is acting like a battery or acting like a cell. Or what kind of cell it is? It is the, let me draw it here. It will be somewhat like this. That will be kept somewhat like this. Yes or no?
Yes, sir.
Yes.
This is something that will be, this rod is going to behave like. And if it is behaving like this, so what is the potential difference between the extreme ends and the center? That is the same. Why? Because this is nothing but the batteries are connected somewhat like this in the parallel. So what is the potential difference across these two terminals? That is same as V, whatever is of one.
Yes, sir.
Yeah.
Understood,
Yes.
both of you? Yes. So
Yes,
this
sir.
is the case, and my eardrops had exactly, it should not happen in the last class. Okay. So this
Yes,
was
sir.
the thing, actually, for the disk that we used to discuss. So for the disk also, we'll get the same answer to be V omega L, whatever you learn VBL by 2. I used to just remember this particular VBL by 2. Okay. This was the
Yes, sir.
thing here. Understood? Is this clear to both of you?
Yes, sir.
Okay. So we'll move on to the next topic, that is the self-induction. Although I had decided this topic and the next topic to be covered in the next class, but as we are remaining with the time, so we'll just start it over here only. Self-induction. Okay, so what is actually the self-induction? Self-induction is actually, it is first of all linked with the inductor. What is inductor? Have you listened about that,
Uh,
both of you?
yes, yes, sir.
What it is?
It generates magnetic field, right?
Okay, so self-induction, it is first of all linked with the inductor. So let me draw a inductor here. It is the circular coil, somewhat look like this.
Mm.
Okay, and what it is, first of all, let us write it over here, that the phenomena, it is the phenomena phenomena of production of induced EMF and induced current in an inductor when current when phenomena of production of induced EMF and induced current in an inductor when current flowing through the inductor changes. The inductor changes. Changes is called self. Okay. Actually, what happens that we used to represent it with a letter L. What is actually happening here? Suppose that let's say that is it looking like a solenoid?
Yeah.
Is it looking like a solenoid?
Yes.
Okay.
Yes, sir.
So what is happening here? Are all the turns of the solenoid are acting like a closed loop because they are very close to each other? Yes or no?
Yeah. Yes, sir.
Is the current
Yes.
flowing across these closed loops? Yes or no?
Yes, sir.
Yes.
If the current is flowing across these closed loops, so do you agree that the current in a closed coil produces the magnetic field? Yes or no?
Yes, sir.
Yes, sir.
If this current changes, so do you agree the magnetic field will also change?
Yes,
Yeah.
sir.
The magnetic field through the closed loop will change. If the magnetic field through the closed loop will change, do you agree that all these the previous story that we are watching from the last 1.5 hours will come into the play, that the flux is being changed from the loop?
Yes,
If
sir.
Yes.
the flux is changed from the loop, do you agree that it will try to resist it, that particular change?
Yeah.
And
Yes.
that actually the phenomena of that particular thing is called L. And when it is going to happen, it is only going to happen as the current through this particular loop will change.
Mm.
Yes, sir.
Okay, so this will come into the play only when the current through the loop will change. Why? Because what is the magnetic field inside the solenoid at the center? B equals to
Mu naught and I.
mu naught
Mu naught and
Ni.
I.
What is we had seen this particular thing in the magnetic field chapter, and what is it at
Yes.
the ends of the solenoid? How much it is?
Mu naught and I by 2.
Mu naught Ni by 2. So did you understood this, that as the flux through the loop will change, so it will induce the EMF inside it? Understood?
Yes, sir.
Yes, sir.
So what actually it is, that magnetic field is directly proportional to the, we can see that these magnetic field are directly proportional to the current flowing through it.
Oh,
Yes
yes,
or
sir.
no? So that is
Yes.
the current flowing. Okay, if it is there, so the magnetic field, do you agree it will be called n times of phi? If the flux through one loop is phi, so the magnetic field through the n loop will be n times of phi.
Yes, sir.
Yes.
Will be directly proportional to the current flowing. Let us assume that the current is I.
Yes.
If it is there, so do you agree that if this proportionality sign, if I'll remove this proportionality sign, I'll place a constant over here.
Yeah.
Yes.
So that becomes n phi equals to L into I. Understood? And this L will become n
And
phi
5 by.
by I. Is this clear to both of you?
Yes, sir.
This is
Yes, sir.
actually the mathematical expression of the uh, self-inductance. Okay. And we
Okay.
basically, we used to define it for the other things also, but mostly you will see that we used to keep this thing in the, for the particular inductor only. Understood?
Yes, sir.
What is N here? N is the total number of
Number
turns.
of.
Total number of turns. Okay, not number of turns, because is it the number of turns per
Number of
unit
turns
length
per unit length. No.
or the total number of turns? Actually, we
Total.
had decided it over in the chapter of the magnetic field only, that whenever I write N, this is number of turns per unit length. And whenever I write capital N, it is the total number of turns.
Okay.
And this is being followed at most of the places, so we keep this in your mind. Okay, like
Yes.
this, if I had written the magnetic field in the above cases, I'd use the small n there, not the capital N. Okay, yes, Region, because you had
Yes,
not
sir.
studied the magnetic fields with me, that's why I'm just
Mm.
explaining it over here also. Okay,
Okay.
so n is the total number of turns, phi is the flux through one loop. Okay, I is the current passing through the conductor, passing through inductor, current passing through inductor. Okay, inductor you can write. And L is the coefficient of self-inductance. What it is? Coefficient of self-inductance. Or what you can say, that it is the self-inductance simply. Understood? Is this clear to both of you?
Yes,
Yes,
sir.
sir.
What next we can write? As we know this, so do we know that flux equals to Li by N.
Yes.
Can
Yes.
we write it like this? So
Yes.
if the current through it changes, that means I changes. So if the I changes, do you agree that the flux will change?
Yes.
If the
Yes, sir.
flux will change, so do you agree that the EMF will be induced?
Yes.
Yes.
So how will you get the that induced EMF? Do you get that the total flux is the N phi is L into I?
Yes, sir.
For to get the total EMF, do you agree that I need to N times of D times of dt by total flux?
Yes.
Yes or no?
Yes, sir.
Yes.
If I differentiate it over here, what will I get? Is I'm going to get the uh, that particular see, just place
Faraday
it
law.
over here. What will I get? Can I take out the L out of it? Yes or no?
Yes.
Yes or no? Can I take out the L out of the differentiation? And
Yes.
suppose
Yeah.
let us take for the easy one. Let us take that N is equals to 1. So flux will be Li
Okay, yeah.
simply. If flux will
Yes.
be for the simplicity purpose, I'm taking the phi to be 1. It will be total flux L times of I. So what will I get? Minus of L times of di by dt. Will I get the EMF like this? Yes or no?
Yes, sir.
Yes.
And this is the expression across the inductor for the potential difference. If the flux is I inside it, if the if the current passing through it is a function of time, so the EMF induced across it will be minus of L times of di by dt. Is this clear to both of you?
Yes, sir.
Yes, sir.
Yes, that's it. This is the expression of the EMF, and that's it. That's keep it till here only. And we are having the class tomorrow also, no?
Yes, sir.
Yes.
Tomorrow we'll see some of the questions over this particular topic, and that's it. I'll assign you the homework also today, and that's all about the today's class. If we'll cover it up tomorrow, and in the from the next session we'll start with some other chapter. What chapter do we were supposed to start?
Sir, I thought we have exam next Monday, so could you like do some important questions with us in class?
Important question. We can have that session also. Uh,
Yeah.
but it's all your call. Whatever you people think that we can go for that. No issues.
Yes, sir.
We can take the good questions also, or we can take the another one, new another one. That's it. Uh, Anything else also. Okay. So
Sir, I had a
whatever you
doubt
people
in this. Sir, could
in
you
this,
scroll up?
yes, 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 please. Hmm. Which one?
It was in motional EMF.
Motional EMF. Where it is?
More up, sir.
This one.
I think yes, sir. Sir, here you had said that there was like some two steps that you wanted to like
Yes,
derive the equation
we
in
were
one step.
trying to expel that out particular one.
Yes, sir.
We don't want
What
this to.
was
I'll give
what
you
were
the
you trying to
exact
explain?
expression, but not today. I try to solve the questions using this analogy because I remember that. Because I personally know na, that people
Yeah.
used to forget that in the examination. That is regarding some dot and the cross. Okay. That is regarding some there are the three quantities. Can you say B, V, L?
Yeah.
All these three are the vectors. Do you know about it?
Yes. No, I
If
didn't.
you,
Yes.
Yes, sir.
yeah, okay, I'll give you the hint. Let us take it as a homework. Take the
Okay.
BVL in such a way that one should be kept here, one should be kept here, and one should be kept here. And
So it'll be
ultimately, yes,
so will it be L dot
ultimately, no, I
L
don't know the
dot.
answer. I don't know the
Okay, sir.
answer. Ultimately, you have to do it so that you get the EMF to be correct version as you are getting it over by solving this complete analysis.
Okay, sir.
Understood? Just I'm
Yes, sir.
giving you the hint only because ultimately these things are going to happen. You'll take the BVL in such a way that two of the cross and one of the dot will ultimately lead you to this particular expression.
Okay, sir.
Okay, so it's your homework to both of you to decide that how to do so. Okay, is this clear to both of you?
Yes, sir.
That's all about the today's class. And if you have any doubts other than this also, you can ask, or else you people can leave. Then we'll see you again tomorrow.
So the battery thing, like how do you know like which side is it, like positive or negative, like
Which side is
terminal?
the positive and
Yeah. You told
which
like
side is the
velocity.
positive?
Yeah.
No, no. Actually, what was happening? First of all, try to understand with this particular case. That was in this case. Okay. In this case, what was happening? That V is moving in this case, so the positive charges are moving in this case, in this side. Sorry.
Yeah.
If we'll do V cross B, just do see the V are moving in this direction. Do you agree with me over this? I'm keeping the plane over this particular screen, keeping our hand
Yes, sir.
in this screen. V is moving along this. Do you agree?
Yeah.
Should I cross the B? That is, B is pointing inside the screen. So B will
Yes.
be this. So is my
Yeah.
thumb pointing in the downward direction?
Yeah.